I mentioned before we were going to look at a tool which will help us work out probabilities of the normal distribution. And in this video, that's what we're going to do. That tool is called the standard normal distribution. Say it is known that the height of Australian men follow a normal distribution with mean 175 centimetres and standard deviation 11 centimetres. What is the probability that an Australian man chosen at random lies between 164 centimetres and 186 centimetres? Well, what do we know about the normal distribution? I just said in the last video that 65% of all values lie within one standard deviation of the mean. One standard deviation below the mean is 164 centimetres and one standard deviation above the mean is 186 centimetres. That interval we are looking at is entirely symmetrical around the mean, and every value there is within one standard deviation from it. And so the probability that an Australian man chosen at random is between those values is 0.65, because we know 65% of Australian men lie within one standard deviation of the mean. How about though if we were asking this? What is the probability that an Australian man chosen at random is between 150 and 177 centimetres tall? Now this is not symmetrical around the mean, so we can't really say much. How would we work out this probability? Let's leave this question for now and come back to it, and let's talk about a particular type of normal distribution. Let's talk about this normal distribution which has mean 0 and standard deviation 1. This is called the standard normal distribution, and we know a lot about it. We know a lot about it because mathematicians before us have researched a lot about it. And one of the things they've done is written down all the values of the CDF of this. So we've got, for every possible value that Z can take, for every possible alpha, we've got the probability that Z is less than or equal to alpha. And we can find that CDF by looking at statistical tables. And this is the statistical tables that I've included in your course notes. This is the normal distribution function. We can read this in the following way. So say we wanted the probability that Z, which is a standard normal variable, is less than or equal to 0.62. Well, the way we would read this is we would use the rows to find the first decimal point, so 0.01, 0.2, 0.3 and so on. So we go down to the row which represents 0.6, and then we can go over and use the columns to represent the second decimal point. So we can go over to 0.62, which is the 0.02 column and the 0.6 row. So the probability that a standard normal variable is less than or equal to the value 0.62 is 0.73237. And we actually have nearly every value here. We start off at 0 and we have all the values right up to 2.79. We only have the positive values, but that's because we know that the normal distribution is symmetric. So we can use the properties of the normal distribution to find the negative values. Okay, so normal tables give us the CDF of a standard normal distribution for positive values of alpha, from 0 right up to, was it nearly 2.8. If we wanted the probability that Z is above alpha, then we can use the following identity. And where does this following identity come from? Well, if we think about that the PDF is the area under the curve, we can start doing geometry with that. So the probability that Z is above alpha is this area under the curve above the value alpha. And if we only know the values of below that, we can say that that is all the area under the curve minus what's below alpha. So what's above alpha is everything minus what's below alpha. What is everything? The probability of everything under the curve. Well, these are probabilities, so that must be 1. And the probability of z being below alpha we can read off the tables. And so even though these are not written in the tables, we can still work them out. Similarly, because we know the normal distribution is symmetric, if we wanted negative values, then the probability of z being above alpha is equal to the probability of z being less than minus alpha. And if we want z being between two values, so between two values, well, what do we know from the tables? We know the area under the curve below a value. So we can say that is the area under the curve below the highest value minus the area under the curve below the smallest value. So we can do that geometry, convert that back into the maths, so that gives us the probability of z lying between alpha and beta is the probability that z is less than or equal to beta minus the probability that z is less than or equal to alpha. And now we can work out nearly all the probabilities associated with a standard normal distribution. But that's only useful for the standard normal distribution, when z has a normal distribution with mean 0 and standard deviation 1. Think back to our Australian men. Their heights followed a normal distribution with some arbitrary mean and some arbitrary standard deviation. So in order to make use of the standard normal for an arbitrary normal distribution, we need to transform it in some way. And the transformation we can use is this. If x is a normal distribution with mean mu and standard deviation sigma, then z is x minus mu over sigma, and then z has a standard normal distribution. Think about what we're doing here. We are taking mu away, we're taking the mean away. So what is that doing? We're taking that standard normal curve and shifting it along the x-axis to 0. And then once we've shifted it, the width is still wrong. So we can scale it down or stretch it out by dividing by the standard deviation, and that makes the standard deviation 1. So we are shifting it and scaling it. Now we can work out any probabilities for any normal distribution. So let's go back to our question. The height of Australian men follow a normal distribution with mean 175 centimetres and standard deviation 11 centimetres. What is the probability that an Australian man chosen at random is between 150 centimetres and 175 centimetres? So in order to do this, we need to transform this to a standard normal and work at the probabilities from the standard normal. So let x be the height of the randomly chosen Australian man. It is normally distributed with mean 175 and standard deviation 11. We can transform this to the standard normal with the following formula. X minus 175 over 11. So now what was the probability that we wanted? This is the probability we wanted. How would we write that now as the probability in terms of the standard normal? Well, we have this transform, so we'll apply this transform to everything. Okay, so now we have something that looks familiar. We want the probability that z is between minus 25 over 11 and 2 over 11. So remember our standard normal tables, they were in decimal places. So let's write this as decimal places to make it a bit easier. And now we have z being between two values. So we can take the probability of z being less than the bigger value minus the probability of z being less than the smaller value. Okay, this term we can read from normal tables straight away. This term needs a bit of work. We have a negative in there. How do we transform that negative? Well, we know because it's symmetrical, we can say that that is probability of z being greater than or equal to the positive version of that. The CDF doesn't give us z greater than, it only gives us z less than. So how would we transform that? Well, that would be 1 minus probability of z less than. And now we have 3 terms, this, this, and this, that we know. This is just one, and these 2 we can read from standard normal tables. So reading from standard normal tables, we get and that gives us a probability of so the probability that I will pick an Australian man whose height lies between 150 centimeters and 177 centimeters is 0.55982. So that means that about 56% of Australian men lie between 150 centimeters and 177 centimeters.